Here you can see this figure. The dark gray is equals to cutting speed Vc, red equal to feed F, light gray cutting depth AP, A diffusion, B mechanical abrasion, C scaling oxidation, D tilt up edge formation. Abrasion is the process by which particles trapped between two sliding surfaces cut, score and gauge material from a softer machine surface. A good example of this would be how sandpaper cuts steel. Corrosion, where is the result of a chemical reaction that is accelerated by temperature. It is typically caused by moisture or another corrosive liquid or gas. Dust or oxidation is the most well-known form of corrosive wear. Fatigue, wear is a consequence of subsurface cracking which is caused by cumulative rolling, contact loading of rollers and pitch lines of wear of gear teeth. Fatigue causes chunks and platelets to break off, causing further wear as more contact occurs. Adhesion takes place when the load between moving surfaces is transferred by metal to metal contact, causing friction. Lubrication is used to prevent this, but if lubrication is inadequate, then friction rises to very high levels. In addition to these four root causes, there are a number of other mechanisms that in particular applications can contribute to component failures in industrial machinery. These include surface erosion, electrical discharge, cavitation, and material deposition. All forms of wear can pose a significant threat to the health of your wear and the productivity of your operations, and uniformity. Identifying them can be extremely difficult, so the damage to the machine itself and to your productivity could be done before you are even aware of an issue. What are the wear reduction methods? We all understand that wear can only be mitigated, not prevented. We can minimize wear, but we won't be able to eradicate it. Many strategies have been devised to minimize wear, as detailed below. Prevention of overloading. Overloading should be avoided since it causes lubricants to break down and puts an excess force on the worn surface. Maintain a proper clearance. When the clearance between the surfaces is too small, a lubricating oil layer cannot be applied to the worn surface, resulting in metal on metal contact. If there is more space between the surfaces, motion is lost. Due to the sheer absence of lubrication, machine's parts wear down quickly, making it loud and vibrating. Better lubrication. Lubrication produces a lubricant film in the space between the contacting surfaces, which improves its smoothness and avoids material contact. Improper lubrication leads to wear of surfaces. improper improving the surface fishing. Various sorts of straight or circular layers are formed when parts are passed through the machining process that cannot be seen with the human eye. Because of the good surface, a line contact rather than a point contact is created, which is advantageous in processes. Good surface finish uniformly distributes load rather than maintaining asperity contacts, leading to reduction of wear. High surface hardness in comparison to soft surfaces. Hard surfaces wear down faster. Heat treatment is used to enhance the surface hardness to the shaft bearing and guide way, which reduces wear. Proper surface treatment. Mechanical wear can be minimized by applying a hard proper surface treatment. Mechanical wear can be minimized by applying a hard coating of metal such as chromium or galvanic on the surface. As a result, it may be argued that if a hard layer is applied to the surface of a wear-resistant metal, the part's wear can be minimized.